All right. So for me, my name's Brady Rogers, and my group decided that I'm going to do objectives or minors 3.2 to 3.3, with 3.2 just being the differences in a modern approach. We basically, this is going to be under the second law of thermodynamics, and working through, as you can see through the bullet points. We said, or I said, initially focused on heat engines, now encompasses broader systems, including biological and quantum processes. Um, Entropy definition. I wanted to add this in here so you can kind of get a better understand of why this is going to relate back to the modern approach. Entropy is basically a measure of disorder, now understood as a fundamental aspect of information as or in energy dispersal. Sorry. Um, Basically, entropy is the heat being used as energy. So any, I guess you could say, like factory or certain types of machines that give off this certain type of heat can be used again for whatever reason for energy. Um, Statistical mechanics, early interpretations were microscopic. Modern views incorporate statistical mechanics to explain how explain microscopic behavior. Um, this is just relating back to the idea of the modern approach. Um, it's ongoing, you know, type of ordeal where each and every day we learn something new about whether it be or entropy or how heat can be transversed into being used as energy. The only thing is it's irreversible. Uh, Once seen as a strict rule, now recognized as a tendency with expectations in quantum systems. Once this method occurs, it's now irreversible. Um, it's expanded from classical physics to inform fields like cosmology, information theory, and complex systems. So this is just all going to relate back to the modern approach and the differences between them. Moving on. Modern benefits of this discovery. Uh, as you can see, got a pretty cool picture right here that you can kind of gauge for yourself on how it's kind of like an illustration on how it's going to work. Heat right here moves through, bam, to the next point. Uh, Heat engine. This can be used to convert the heat, and then you see this little area right here. This is going to be your work where it can be transversed. Uh, Moving on, heat moves naturally from hot things to cold. It's pretty well known. It's common sense. Put a coffee cup on a table. The heat's gonna move to the coffee, or gonna move to the table. Some processes can only go one way and cannot be reversed. Like I said before, you can't really reverse it. It's irreversible. Not all heat can turn into work because some energy will be lost. True. This is why we have this right here, a heat engine, which can make some of the heat become useful. Heat engines use heat to create work, as shown right here in the diagram. You can see that heat right here is going to go through. Some's going to be left right here, which is irreversible. This right here is going to be your work from the heat, and it's going to be used for whatever means. Efficiency depends on how much heat goes in and also how much is lost. This is going to be where you're going to put in your equations like this, your work, and this is going to be your hot and your cold. You just subtract the two, and that's going to give you your total efficiency. You know, I mean, it's kind of self-explanatory. You can kind of gauge it for yourself on how you're going to be, you know, the heat is going to be turned into actual work, and then the heat that is lost is just going to go to the cold area. Okay, moving on. 3.4, future expectations of research. Um, this is all going to relate back to what we've been talking about here. As you can see, it improves energy efficiency in engines and machines. Like I said before, each and every day we're finding out new ways to really um, get the upper hand with you know making heat as a reliable source of energy. Um, can create better refrigeration and cooling systems, and I feel like this has been one of the really main concepts that our group was really harping on, and you'll see later on in the presentations where we actually use it as an example. It's just a really self-explanatory type of explanation on how the second law of thermodynamics really is comes into play, and it can really just give you a clear insight of what's really going on. Um, Moving on, advanced renewable energy technology. Uh, that's kind of what we've been talking about here. It's all about how we can benefit from the heat that is made, how we can use that, for further, production, whatever it may be. Just efficiency is really what is kind of the whole concept of the second law of thermodynamics. Like, what can we do to further improve from something that may seem like as a loss? Kind of just what can we do to further benefit everyone else through something that may seem as a loss. Um, Study thermodynamics in quantum systems. Um, that just relates back to a lot a lot more broader spectrum. Um, this is where a lot of the equations are going to fall under too, on exact calculations. You'll see later on in slides how we were able to kind of correlate the equations into the second law of thermodynamics. Improve heat management in electronics. This could be anywhere from overheating, um, just the overall efficiency of machines itself. Uh, this heat that is made from these machines can be turned back into something into those machines that can further help it for better improvement on whatever the machine is designated to do. Support space exploration technology. This is pretty straightforward. Like I said, this heat that is made from anything like engines, toasters, anything given off that type of heat is going to be the same way for your bigger machines like rockets. This can be if we're able to really nail it down to the T on it, we can find out a way how to really explore further by just figuring out something as in the second law of thermodynamics, and it's improving every day. Develop new materials for energy transfer. Like I said, it's ongoing, so every day there's going to be new inventions that can further improve the heat loss, theory, the entropy behind it. I do believe that there's going to be a point where um, we're going to have something come out where it's going to really be a game changer in you know the way we're able to understand the second law of thermodynamics. And I do believe that once we do find something that can really change the heat from just being a waste to energy, it's going to be a game changer. And not only just that one invention, but it's going to be a, like a revolutionary cause, because it's going to translate to anything else that's going to be, that falls under the basis of the heat loss, the entropy. Um, Help address climate challenges or climate change challenges. This is a really big one because, I mean, most people, I would say majority of people do believe in climate change. As you can see throughout the years, there's been lots of reports of, the icebergs melting. The weather's changing. The weather's different than it was 50 years ago. It's a ongoing process, and I think a lot of it has to do with human production. Whether that be just cutting down trees. I mean, it's a known fact that humans being here on Earth has changed the climate, just because there's things in Mother Nature that need to occur that humans put a pause on that can affect the climate. So with these slides done, I mean, I could go on for quite a while about this, but it's everything that I said just kind of relates back to the second law of thermodynamics, and um, how we can further better the future of humanity by just figuring one small thing out, which can correlate to a big thing. So yeah, hopefully we keep on keeping on with the second law of thermodynamics and everything that goes into it. Thank you.